Today we're going to talk about everybody's favorite. It's the Born-Haber cycle. And you have to know quite a bit of different things to kind of understand how this works. So I teach in analogies, and for this, it would be like building a house. You don't just have a bunch of materials and then poof, you have a house. There's certain things that have to happen, and they have to happen in a certain order. You can't put the walls up and then put in the foundation. You got to dig the foundation, you got to lay the electricity in the pipes, you got to pour the foundation, then you work on the walls, and then you work on the roof, etc. So understanding the different pieces that have to happen and understanding the order in which it has to happen is really important. So we're going to start off with just an example. First of all, the Born-Haber cycles that you get will be heater formations for a binary ionic compound. You'll get either group 1 or group 2 metal, and you'll get either group 16 or group 17 nonmetals. In group 16, oxygen is diatomic, but sulfur is not. In 17, they're all act exactly the same. And we know to crisscross charges to form the ionic compound. So sitting in front of you is the equation for heater formation for sodium chloride. It's not balanced. Balancing is a different thing than knowing what to put in and the order to put it in. We do have to balance it because in thermodynamics, if you have twice as much, then the delta H will be twice as much. So we have to take into account how much we have, but first let's figure out what we need to do in the first place. So this equation says that we have solid sodium metal that's going to react with the gaseous diatomic chlorine to form an ionic compound called sodium chloride. If you're new to chemistry, the sodium solid on the left and the sodium solid on the right look really much the same, but they're not. They're completely different. First, let's look at what the compound looks like for sodium chloride. Sodium chloride is not just NaCl, it's Na plus and Cl minus, and they're hooked together in a very large matrix of very organized alternating plus minus plus minus, as you can see from the model on the right. When you put these together, you have to put together them one by one. And if they're one by one, they must be in a gas. And for the ions to hook together, they must be gaseous ions to form this solid. So that is the key last piece that we'll talk about in a minute, is that you can't hook up a sodium metal that's uncharged, put it together with a chlorine, and then make it charged. They wouldn't stick together because they won't be opposite charged. And once it's in a solid form, you can't take off the electrons off each one separately. They must be separate to take off the electrons, which is also something we'll deal with. Starting with elemental forms, and the elemental form of sodium is a metallic form and solid. So you have this positive cations and a sea of negative electrons. So we have to form a sodium ion, which means we have to remove all of these electrons to make them ions. You can't do that in a solid state. You can only remove the electrons in a gaseous state. Chlorine is a diatomic molecule. It is covalently bonded. So if we wanted to make this into an ion, you can't make Cl2 into an ion. Now, it is already a gas, so we don't have to worry about that. It would need to be a gas, but it is. And to put an electron onto the chlorine to make it chloride, we have to add an electron. You can't add an electron to Cl2, you have to add an electron to Cl. So to do that, we have to break this covalent bond. Every one of these operations requires energy, or you might get energy out, but there is an energy change with each of these operations that we'll deal with, and there is a sequencing of these that need to be in order. In the end, we're just adding them up. So there's no order in addition, 2 plus 3, 3 plus 2, it's the same. But for us to understand how it goes, I think it's important to understand the sequence. We have to deal with the sodium, we have to deal with the chlorine, and then we have to deal with the sodium and chlorine forming together. That is our task. Way to show the Born-Haber cycle. I don't think it's the most clear way, but this is a different rendition of Hess's law. The up arrows are endothermic, the down arrows are exothermic, and this is why it's a cycle, because the left side and the right side add together in terms of magnitude. Um, so we'll put these together, but I prefer to do it as more of a Hess's law. It makes more sense than this one. Um, that's what we'll do next. So we're going to add multiple equations up to equal this one. So this is our final answer, is solid sodium plus diatomic chlorine forms a sodium chloride ionic compound, which means they're ions. So what do we need to do with the sodium? The sodium, first of all, needs to go to a gas, and then it needs to be ionized. Chlorine is diatomic. So first of all, we have to break that diatomic piece. So that's going to be bond energy that we're talking about in terms of the change in energy when we do this. It's already a gas, so there's no phase change needed. Now we have separate chlorine atoms, and we have to turn them into an ion. This is not ionization energy. This is going to be electron affinity as the energy change. Next, we get the sodium ion that we've created and the chlorine ion that we created, and we're going to put them together to form the compound. So this is the binary ionic compound as a solid. So each of these pieces are what we need to deal with. And if you add up each of these changes in energy, you get the overall one. Now, while it's a lot, you can see the changes that need to happen. If you have a solid, it needs to be a gas, then that's going to be sublimation. If you have uncharged, it needs to be a positive, that's ionization energy. If you have a diatomic molecule, you have to break it. The energy required to break 1 mole of a covalent bond is called bond energy. These are all definitions, and to understand Born-Haber cycle, you need to know the definitions of ionization energy, electron affinity, bond energy, lattice enthalpy, etc. Here we have the finished product of everything. We don't have numbers included, and that's fine. But if you see, first of all, this is what I like to call the cornerstone of it. This is what the last piece is. Well, it's a sketchy square. And in doing so, it really lines it up so that we can figure out what to do. So we're going to start off with our end product. This is what everything's going to add up to be. And then we're going to go to the opposite of lattice enthalpy. Again, back to knowing definitions. Lattice enthalpy is the energy required, meaning it's a positive value, to break apart an ionic compound into the separate gaseous ions. Well, we're going to do the exact opposite. So it's the same value. However, we're going to change the sign to a negative. So lattice enthalpies are usually very large positives. Now, if you do that, then you can set the whole thing. Or you can go back to kind of what I talked about, and that is this is a solid piece of metal. We're going to make it into an ion that sticks together to form a solid, and therefore it needs to be a gas before we make it into an ion. So here we're going to make the solid into a gas. That energy required is the heat of sublimation. And then we're going to make the gas, the atomic gas, into an ion, and that is ionization energy. If we had a group 2 metal, we would do another one that would be I2, or the second ionization energy. Sometimes they give you a combination. They'll say this value is I1 and I2, and therefore you just use that. And now the metal ion is ready to attach. It is a gaseous ion, so we're all ready to go. The chlorine needs to be a separate ion to form this compound. So we need to separate it and we need to make it an ion. So here we're going to separate it. These are all defined as per 1 mole. That is the definition uh, for any kind of thermodynamic thing. It could be per balance equation for other ones, but these are all per mole. So we're starting with a mole of chlorine gas, not a mole of product. So we start with this, and to break 1 mole of bonds, which is what we're doing, this is the value right here. Now I'm not showing you numbers because in the end, you're just going to add them up. It doesn't matter what the number is. You're going to use a calculator to add them up. But understanding the concept is really important. So this is 1 mole. This is how it comes out, and we have to understand that later when we deal with the actual addition for everything. Now that we have them separate, we're going to get the separate chlorine gas, which is already a gas. We're going to add an electron to it to form the ion, the anion. This is going to be electron affinity. This is per 1 mole. So we're having a mole of chlorine atoms. And then now we have the chlorine ion, we have the sodium ion, and we're going to put those two together to make the sodium chloride, and this is lattice enthalpy. Again, technically it's a positive version. We need the negative one, so we change the sign. The last thing we need to do after we put all stuff together is make sure everything adds up. And in this case, it doesn't, because we have 2 chlorine atoms here and we have 1 chlorine atom here. If you looked at this down here, the balanced equation for this would be like a 1/2 in front, and therefore we put a 1/2 in front. That makes this a 1, and it's going to cancel out. And that means we need to either divide this by 2 or multiply by 1/2, which is the same thing. And when you do that, these all will add up to be this one. The question is either I give you all of these right here and then ask for this one, or I will give you this one and I will give you these and I'll add up for one of these. Or technically, I could give you all but one and you can figure it out. At this point, it's baby algebra 1 and you should figure it out. Clearly, setting this thing up is the hard part, and then making sure the stoichiometry is in place. You almost always have to do a divide by 2 or multiply by 2 at least once, and usually only once. I hope this is helpful. You just got to practice, and if you ever want to put one together and then send it to me and let me check it, I can see exactly what you're doing right and doing wrong, and we can fix it really quick. Thanks.